connect up. At any rate, this is the ASEG webinar series, and Adam is going to be talking about new technology in airborne TEM for deep and covered targets with Western Australia examples. I'm going to just talk fast. So if my laptop's going to, there we go. So I'm going to thank our corporate members. These are corporate members are members that provide us with money and support across the entire Australian regions. And so we've got corporate plus high size, total seismic and bell size, and corporate Southern Geoscience and Santos. Really appreciate them because they're really helping us prevent this talk right now. And we've got a lot of brand sponsors too that really are helpful. WA, where I'm from, I'm the WA president, Todd Majeski. We have very much a lot of help from these people, and you can see SA and NT and New South Wales also have a bunch. So sorry about the speed, but we want to get through and get Adam's talk running. Now, in terms of housekeeping, etc., if you have a question, please go down and click down below and to the Q&A and type them in, and afterwards we can try to have Adam answer those questions. Upcoming webinars next Tuesday, we've got Professor Megan Miller on continental subduction in the Banda Arc, and Dr. Allison Kirby in a couple Wednesdays after that on lithospheric architecture and mineral potential for magnetotellurics. Both of them will be pretty neat talks. And you can see there's a big variety of different talks that we give here. Member benefits, well, maybe I'll zip through these quick. Some of the things that I do like, of course, is we have a good technical journal. We have a lot of job advertisements, which can be helpful nowadays. Good annual wine offerings, which I've taken part of once or twice. And social events and networking, professional networking, very important. And we have nice research funding and travel scholarships for students. And in our case, WA, we do some very good things. Things I like, we have free membership for students. So if you have any students that might be interested in geology or geophysics, let them know about this. They get in for free and they can see all this kind of things. And so there. Now, yeah, we're on, we have a website and we're on Facebook and we're on Twitter and we're on LinkedIn. Neat thing is we'll have these webinars like this out on YouTube, where you can probably hear me babble real fast while I'm giving these talks. So now with that, I'm going to introduce Adam, and this is his bio, and we'll read aloud here. So Adam's been involved in electrical methods for environmental and exploration applications for 15 years. He completed his master's in geophysics from RMIT and got a PhD in physics and geology at the University of Toronto. He's been involved with airborne EM research, both in frequency and time domain, and with CG multiphysics for the past 9 years. So with that, I'm going to switch over, and Adam should now be able to bring up his presentation and start off. Thanks, Adam.
Hi, thank you, Todd. So I'm just going to wait for it to let me share my screen.
Are you able to share your screen there, Adam? Fabulous.
Okay, perfect. We can see the title slide.
Yes, looks great.
Thank you. So I'm going to talk today about the Helitem² system, an airborne EM system that has been acquiring low base frequency data. And this is really useful for exploration in covered terrains. A brief introduction and outline what we'll be talking about. I'll introduce the system. And just, sorry, one last question. Are you able to see my mouse?
Yes, we are.
Thank you. We'll go over some of the technological improvements that let us acquire low base frequency data and some of the work we've been doing with the Airborne EM system. We'll look at why we want to do these improvements, and I'll show a low base frequency example from West Australia for a graphite project. So this is the Helitem² Airborne EM system. We have a 35-meter diameter transmitter loop with a concentric receiver. There's an IMU to measure system attitude and a GPS. The system is designed for high spatial resolution to explore for conductive targets, in particular very conductive targets, and to look through conductive overburden. And the big innovation of this system is an all-new receiver, and in particular, an all-new suspension system. And this suspension system allows us to lower the base frequency. So Airborne EM has typically been the lowest that it could do is 25 hertz. We're now operating at 12.5 and 6.25 hertz. And this is the technical innovation. By redesigning the receiver suspension system, we're able to reduce coil motion. And whenever the coil is moving in the Earth's field, it's going to cause an electrical noise. So the orange curve here shows our previous receiver coil with its suspension. So we can see the noise level through here. And we're going to be operating at 25 hertz. And this is a high altitude power spectral density from the receiver. And as we look at lower frequencies, we start to see the effect of coil motion. With our redesigned system and our new receiver coil, we've lowered the electronic noise and we've decreased the resonance of the suspension system, such that we don't see this increase in coil motion noise until lower frequencies. Now in the past, we could have easily, the electronics are there to operate at low base frequencies, but the penalty would be a dramatic increase in noise. With our redesigned system, we don't see that, or the coil motion noise is nearly as important. So we can do low base frequency. Why do we want it? I'm sure most people know about this, but there's two main reasons. We want to have a longer measurement time so that we can wait for the response from conductive cover to dissipate so that we can see deep, strong conductors. With more off time, we can also better resolve the properties of very good conductors. We also want low base frequencies so that we can have a wider pulse. And this is from a paper by Liu. A wide pulse better energizes strong conductors. So the response from a strong conductor is proportional to the area under the curve. So if we can double the area to 12.5 hertz or quadruple it to 6.25 hertz, we're going to have a higher response from strong targets. So this is looking at the benefits of a wide pulse. I'm showing the response nomogram. So this is just the response for a channel 100 microseconds after pulse end for 3 different waveforms, basically a 25 hertz, 12.5 hertz, 6.25 hertz, for a range of target conductance values. So for resistive targets, we have a small response. As our conductivity increases, our response function peaks. And as we get to very, very strong conductors, the response actually starts to decrease. But you will note that for the wider pulse, the response is higher. And at very high conductivities, it is twice as high for a doubling of the pulse width. We can change to a later time. So this is the last time channel of a 25 hertz system. We see the similar thing, low response, peaking, and then the wider pulse having a stronger response. So it's going to be better at detecting strong conductors. And just the benefits of longer off time. What I'm going to show here is a sort of synthetic 25 hertz data. We flew a 12.5 hertz survey, and in this panel here, I'm showing I've just cut off the off time to look as if it was a 25 hertz. So we have the channels from 5.5 to 9 milliseconds after the pulse end. If we show the full data, we get a different interpretation. So this is dominated by the cover response, and as we use the entire 12.5 hertz measuring time, we can see a basement conductor become evident. So we've done some modeling for trying to detect targets under conductive cover. So I'm just going to sort of talk about the process that we use and show a few examples. What I'm going to do is look at the case where we're trying to find a very conductive target beneath thick conductive cover. So my cover is going to be 250 millisiemens per meter, or 4 ohm meters, and I have a 250 by 250 meter flat line target. And I'm going to change its conductance from 200 to 500 to 1000 Siemens. I'm going to perform forward modeling with Leroy Air, and then add synthetic noise. And then I'm going to apply a spatial filtering in the same way that we would do with Helitem² processing. And this is a 3-second filter in the early times to a 9-second filter in the late times. And the filtering effect is important here. It's not only going to reduce noise, but it's also going to modulate the signal to a certain extent. And the little graphic here shows the forward response in black, and then the effect of the filtering. So if I have a 3-second filter for here to 150 meter deep target, there's not much difference between the forward response and the filtered response. Once I move to a 9-second filter, I'm starting to smear some of the energy out and reducing my amplitude of my peak. If I go to very wide filters, I'm going to reduce my noise level, but I'm also going to decrease the amplitude of my responses, the things that I'm interested in. So there's a trade-off between filter length and fidelity. So it's important to find out what filters are being applied to your data. So a bit of a complicated slide. I'm going to be looking at 25 hertz on the left column, 12.5 hertz in the middle column, and 6.25 in the right column. And what I've done is calculated the response to a target that's 100 meters deep with 100 meters of 250 millisiemens per meter cover. So in the bottom panel, I'm showing the response as a function of off time. And actually, you can't see here, but the solid black line is the target response, and there's a host response is this dashed line. So for this particular target, there's really not much difference between my target response and my host response. I also have the noise level in this gray line. In the top panel, I'm showing the target to overburden ratio. So this is the target response divided by the overburden plus the noise. So basically, I want it to be far from 1. If it's 1, my target is equal to my overburden. For high ratios, I'm going to have a good chance of detecting that target. So for this target, my 25 hertz system isn't going to be able to do a very good job. There's only a small response from my target. As I lower the base frequency, I can see I have a higher target response. And this presentation lets us see at what time channel the response is going to be peak. So it hasn't quite peaked for the 12.5 hertz, but we are through the peak here for the 6.25. The 6.25 has a slightly better chance of seeing this target. Now, this is one way of looking at it. I'm going to look at the profile view next. So this is looking at calculating the forward response, adding synthetic noise, and then filtering the data. So you can't see the target in the 25 hertz, and you can see an increase in the 6.25 and the 12.5 hertz where the target is. Now, if there was a highly variable cover, this amount of signal might not be evident. So I'd sort of call this is a marginally detectable case. If we increase the target conductance to 500 Siemens, the 12.5 hertz has about the same response. There's not much difference with the overburden. I get a little bit higher response from my 12.5 hertz, but significantly higher response from my 6.25. So now I have good separation between my target and my post. And if we look at the profile response, the target is very evident in the 6.25 hertz data and detectable with 12.5 hertz and just not detectable with 25 hertz. And for a very conductive case, my 6.25 hertz still has an increase in the signal, so it's even more readily detectable, but there's no we've already reached the peak of our 12.5 hertz, so it's not going to improve my detectability. I'll quickly show an example from Forestania where there's a very, very conductive target. And I'm going to compare two different iterations of Helitem. So we flew this back in 2012 with a high power system, a 1.5 million square pulse compared to a 12.5 hertz Helitem. So around 560,000 amp meters squared with this wide pulse. This is the results from 2012 with the 1.5 million half sign. So this is the IR2 target with a conductance between 5,000 to 10,000 Siemens. So we're readily able to detect the target. You can see some of the noise from the system out here. There's only thin cover. So we have some noisy late time data. I'm showing from 5 to 13 milliseconds after the end of the pulse. Now the half sine waveform doesn't have much high frequency energy, so I'm not able to very well resolve the near surface information. I'll show the next slide, the more recent results with the Helitem² system. So again, we're clearly imaging the IR2 target. I'm now better able to resolve the near surface layers because I have a lot of high frequency energy from my sharp turnoff in my square pulse. You can also see a dramatic improvement in noise. So even though my moment is about a third with this system, I have much better signal to noise ratio and I'm better able to see this very conductive target. And that's a function of the pulse width. Let's look at a graphite exploration project for Comet Resources. This is near Hopetown along the coast in Western Australia. They are in an active drilling phase to try to define the resource volume. So this work was with Southern Geoscience and Greg Maud. The proposal was to use time domain to determine the electromagnetic properties of the country rock, the groundwater, and try to find cover thickness and determine properties of the mineralization. The idea was that by mapping and modeling the mineralization, that Comet Resources would be able to reduce drilling costs and improve the exploration time frame, so more quickly and more efficiently determine the resource volume. So Southern Geoscience conducted a test ground EM survey over a known target, and this provided clear evidence that EM would work. So by looking at the decay curves over top of the known target and away from the known target, they were able to show that the elevated response, that's this line here, compared to the host response, this power law of decay, that the EM response was due to a confined bedrock conductor, and it wasn't associated with saline groundwater or cover. And modeling this target, they showed that the conductor dips moderately to the east and was very near surface. It was very strike and depth extensive and had a conductance of around 1200 Siemens. So because the ground EM worked, Comet decided to use an airborne EM survey to quickly map the entire project area. So this was flown at 12.5 hertz with a 50% duty cycle, 20 millisecond pulse width, 20 milliseconds of measuring time. The moment was around 560,000 amp meters squared, and we flew about 530 line kilometers over 2 days. A little bit of a background on the Springdale Graphite project. The initial discovery was found from drill sampling, and this detected graphite in the so-called western zone. They then flew an aeromagnetic survey, which led to the discovery of the northern area resource. And they did a lot of drill sampling to define the resource around this area. And that's going to be this yellow body down here, this yellow outline. EM has since led to high-grade intersections away from that known resource. This is actually taken from Comet press releases. This bottom image here is the last channel amplitude from the Helitem². And you can see a very good correlation with the known graphitic mineralization. I'm also showing, or this is from Comet, they're also showing some of the boreholes they've drilled that intersected high-grade mineralization. And you can see good correlation with the Helitem² data, the amplitude data. And they've also outlined these areas here as potential graphite targets close to their known zones of interest. So I'm just going to, this is their grid with their choice of color bar. I'm just going to show another color stretch. This is the last channel amplitude on the right and the calculated decay constant on the right, in the middle. So we can see a good correlation with this northern zone. But what's interesting is that the time constant is actually much longer in to the north of that zone. So this is potentially a very good area to try to find another high resource target. Potentially this is much more conductive material. And I'm just going to zoom in on this northern zone and look at some of the profile data and some of the drill hole information. So this is a zoom in of some of the drilling that they've done, and there's a whole bunch of intersections. At this location here, they intersected 40 meters of 20% total graphitic carbon. And if we look at the profile data, it lines up with this peak. I've actually drawn this line a little bit in the wrong location, but the drill location corresponds right with this peak. And we can see CDI in the bottom here. We're seeing near surface conductor. And we can look at the decay curves right where this peak is. We get a nice slow decay, and we have good separation with the host response. And sorry, this inset is just from about here across this peak. So this conductive zone, where the known graphitic resources, comes down this way, and that corresponds to this area through here. So it's not quite as strong of a target. And this peak and this peak, these conductive zones, were what Comet had outlined in red. So this line is much longer than this image here. So these are potential zones to follow up on. I'm going to look at the known target that the ground EM experiment was carried out over. So I'm going to take the Helitem² data and model two separate lines. And here I'm looking at lines that are spaced out by 200 meters. So I've got this line that goes pretty close to this borehole as B. This is on the right here. I've got my vertical component data, my inline component, and my transverse, my ZXY. That's the field data is the black lines. And the model data that from Maxwell is these red curves. And I'm showing this other line here. You can see that the conductivity or the amplitude starting to rotate to the west. And we can see that here where we have an initial peak, and then we have some smaller amplitudes, and that corresponds to this area through here. So I probably need multiple plates to adequately model this, but basically we have one long plate through here that's able to fit the ZXY data from this line and do a reasonable job of fitting the initial peak here. Now this target was about 24 meters deep with a conductance of 200 Siemens, and it was about 800 meters in strike, so very large again. Now this is deeper and less conductive than the ground EM. It actually corresponds in depth a little bit better to the drilling information. So remember, the ground EM was about a 1 hertz survey. So there's still a pretty big difference between 1 hertz and 12.5 hertz. And I think this is why the conductance value is different between the two systems. I'm now going to look at a spot in the western resource zone, another drill hole that intersected a high-grade zone. Here's some of an image from Comet with some of the drilling. I've interpreted this to be about a 65-degree dip. I've taken the Helitem² data and used Maxwell to model it, and I came up with a plate with a dip of 55 degrees and a little less conductive, 150 Siemens, and about 10 meters deep. Excuse me. So a pretty good match with, or a reasonable match with the drilling information. So a little less, we can see that our amplitudes are less in this zone, and we have a smaller conductance as well. So we've flown this with a low base frequency survey at 12.5 hertz. But was this necessary? What extra information did we gain from this? In the bottom here, I'm just showing the channel amplitude grids, 2 milliseconds from the end of the pulse, 10 milliseconds from the end of the pulse. So if this had been a 25 hertz survey, this would be your last time channel. And here, 20 milliseconds after, so the last time channel from the 12.5 hertz survey we did fly. Now this is not really a comparison of 12.5 and 25 hertz because my excitation is still 12.5 hertz. So I'm getting more signal than I would if I'd flown a 25 hertz survey. But all in all, these two grids are pretty similar. Potentially, there's some thicker cover in this southeast corner. So we're gaining some extra information with the 12.5 hertz. We're able to see through that cover to see that there's nothing, or most likely nothing of interest over here. So we went in with certain expectations as to the target conductance, and it seems that the conductance isn't as high as we thought it was. We also had we didn't have that much cover here either. We're able to see through the cover in all the places. And the targets were pretty shallow. Most were less than 30 meters. So we didn't really need the 12.5 hertz, but it hasn't hurt us either. So if we had more cover or deeper targets or higher conductances, potentially the 12.5 hertz would have been pretty useful. So just a summary slide. With the Helitem² system, we've dramatically reduced coil motion noise by redesigning the suspension system. And this allows us to operate an Airborne EM system at low base frequencies without having a dramatic coil motion noise problem. We want low base frequency to increase our pulse width and better energize strong conductors, as well as to have more off time, more measurement time, so we can see through conductive cover. And from looking at our examples, we're able to see that the receiver suspension mitigated coil motion noise and that we can obtain new information with the very late times. And we are currently flying the system in around Perth. So this is just a few of our upcoming 6.25 hertz projects. And we're probably going to be in the area for the next couple of months. And the targets here are very conductive nickel targets. So the examples I've shown aren't one-offs. We're actively flying the system at low base frequencies. Thank you very much for your attention.
All right, well, thanks, Adam. That was pretty neat. We've got one question. I mean, we started a bit late, so there will be, people will have to be leaving. One thing that if you pass on your questions to our ASEG secretary, et cetera, I think we can then, maybe Adam can reply to questions later on, throughout the week or something like that. But let's see, we've got one question. What's the price difference between 25 hertz and 12.5 hertz, Adam? You know?
I don't know. That's not really what I'm doing. It's going to be a conversation with the sales team, but yeah, it's all going to be location and how difficult the areas to get to and all those sorts of things.
Yeah, I was wondering myself, and for me, let's see if there's any more here. Now, in terms of the size of what you're carrying, is there how much bigger are these lower frequency bigger sources than the original 25 hertz?
So we're actually flying it's the same system with exact same hardware. We can do Helitem² with the 25 hertz and 6¼ hertz, and it's the exact same hardware. We're just making some settings changes to generate a different waveform. There is a difference with the older system, and it has to do with that receiver or the suspension system, but that's just the improvement that got us to the low base frequency. Once we're in the field, we can fly both with exactly the same hardware.
Okay, so yeah, so it's more taking advantage of the newer suspension technologies that you can do this. Okay.
Okay.
Questions are popping in now. Let's see. So okay, well, okay, we'll go, what about the impact of the blurring of the response with low frequencies because the helicopter will have moved further with the longer channels?
So that is right, further with the longer channels. Well, we're doing the same stack length. So we basically are, so we're still stacking at say 9 seconds. So we're covering the same amount of ground. We now have fewer repetitions and less averaging is occurring. So there is a trade-off there. You have less averaging, so you do have higher noise. But this is a root and increase in noise. Whereas in the past, you would have had orders of magnitude more noise because of coil motion. So we've reduced the coil motion, and there is a trade-off with your averaging. In areas with strong conductors or conductive cover, it's worth the trade-off. It's worthwhile going to low base frequencies. There are definitely some areas where it's not advantageous. So that's why we like to do a feasibility study and work to see which is going to be the most effective. But the noise increase from that averaging is secondary. That's a minor effect.
I'll take and John Carroll has a question that kind of relates to that in a way. So what's the along the line spatial sampling of the 12.5 hertz then?
The along the lines sampling. So we digitize our data to 0.1 seconds. That's our fiducial. So we're stacking, we're stacking 9 seconds of data. So we're still putting out data every 3 meters. It's just how there's not really much of a the spatial resolution is actually the same between the 25 hertz and the low base frequencies. It's just the number of repetitions that go into that.
Well, and 3 meters then would be that typical spatial resolution then.
That's the sampling. We are with a 9-second filter and a 25 meters per second flying. It's about 150, 200 meters. That's the whole area that you're measuring over.
Right, that makes more sense. Yep.
Yeah.
Long one from David Arnett's good one. Great talk, Adam. Also great to see both Leroy Air and Emit's Maxwell in use, and a demonstration of the need to close anomalies temporarily as well as spatially. Your filters presented in conjunction with Leroy Air modeling are spatial filters designed to average spatial noise. Could you comment on how many typical stations are averaged in the various filter lengths? bit what we were talking about actually. And then are these spatial filters applied to all measurement times? The same spatial filtering at early times as for late times?
Right. So in the early times, we have a smaller spatial filter, 3 seconds. That's what we do for the early times, and we sort of start with 3 seconds and make it progressively wider at later times. So those should be seeing deeper structures. So you can afford to have that wider filter. You're not going to be smearing as much energy. So the short answer is 3 seconds for early times, 9 seconds for late times.
Okay. And then we've got a question. Yep, they said thank you. Cameron Thompson asks, what are the optimal depths of investigation for the 6.25 versus 25 hertz?
So that is a tricky question because it depends on the connectivity. In a resistive area, they will have very similar depths of investigation because the base frequency isn't the determining factor. It's signal and noise. The noise is going to be similar. 6.25 will be a little bit more noisy because there's less averaging. But they'll have similar exploration depths in resistive terrain. When you get to conductive terrain, that's when you're going to see an advantage from the low base frequency. And that's going to come down to exactly what the conductivity is. So it's a bit tough to say, but it's going to depend on the conductivity.
Yeah, that makes good sense to and to them, I'm sure. So thank you. I guess if people are really interested in this, they could be sending you guys specifics about the conductivity that they think they see on their surface areas, things like that, and then they can ask you about penetration and because with the modeling, I think you can decide pretty quickly if you can burrow down past 30 meters, et cetera, this or that, or stuff like that.
That's right. So I showed a few images from a feasibility study that we did, and we looked at different target depths, different target connectivity, and different host thicknesses. And that presentation I was showing with the target to overburden ratio, that gives you fairly quickly a sense of what the exploration depth is going to be. And it's always a function of how big or how conductive the target is.
Mm-hmm. And Sebastian Nixon, nice talk, Adam. Do you think Helitem² technology would have potential to detect, resolve a number of stacked coal seams, CSG targets, where one or more of these seams may intrude, resulting in increased conductivity? Target depths range from 100 to 300 meters.
Without looking at it in detail, I'm going to say yes. We've used the system actually for coal exploration before. There's going to have to be something very, very conductive, some very conductive cover for us not to see 100 meters. There's going to be I think a pretty good chance that it's going to be effective down to 300 meters as well.
And then someone asked, is this all run through Excalibur geophysics now?
No. So yes, we've been purchased by Excalibur Geophysics. That was announced, I guess, last week. For the time being, we are still part of CGG as we wait for that process to occur. I think it's sort of scheduled or hoped to be completed in Q4. So it's still going to be a couple months before it's part of Excalibur.
Well, that'll give people time to figure out the new email that you guys will have. And so if they've got, I'm sure people will have some good questions to pass on about their particular scenarios. Let's see if I can spot anything else here. I think this is what we've, I think we've covered all the, well, I think I'm going to close and reopen just to make sure that I haven't missed anything. I think these are all the questions that we have had been delivered to us now. And so, heck, I thank everyone for showing up for as long as they have. We're down to 8 participants, so I think people are go. And Adam, good that you were able to pull off the connection finally and get on. And thanks for staying up. What time is it there, by the way, before we finish?
It's about 1:15. So yeah, my apologies as well. I don't know what was happening there, but to thank everyone for staying on and for your patience as well.
All right. So with that, I think we'll shut it down, let Adam get some good sleep, and the rest of us carry on with the day. All right. Thanks
Have a
again.
good day, everyone.
All right. Cheers.